Hi, in this video we'll be looking at how to use steam tables to find out entropy at different conditions. So let's look at this table here. First one, let's label that as a first one. And we given the pressure 5 megapascal and temperature as 120. So first thing I want to find out what will be the saturated temperature at 5 megapascal, right? So we're going to find that at table A5, the pressure table. So let's go. Now table A5 at 5 megapascal, which is 5,000. So 5,000, the saturated temperature is 263.94, and our given temperature, however, is 120. It's way less than this T saturated temperature. Then we know this will be a compressed liquid, right? For compressed liquid, the temperature will be less than saturated temperature. Then, because it is saturated temperature, we're going to go to the right table, table A7. So at table A7, we want to look at this condition of 5 megapascal, which is our first mini table at 120 degrees Celsius. And what we want to know is what's the entropy S. So S will be equal to 1.5236, right? Okay, so that's our, by the way, the unit for entropy is going to be kilojoule per kilogram per Kelvin. Okay, so that's the first one. Now let's look at our second problem. We're just going to move on to finish all 5 of them at this video, hopefully. So 2, again, we're given 2 properties, pressure and temperature, following the same top logic. Table A5, looking at our pressure table, we want to find out what's going to be the saturated temperature, right? At 1 megapascal, which is 1000, our saturated temperature, Tsat, at 1 megapascal, it is 179.88 Kelvin. I'm sorry, degrees Celsius. And our temperature here is 50 degrees, way less than this Tsat. Then this is the same logic. It is a compressed liquid. Well, without going to the compressed liquid, which is table A7, because we already know the lowest pressure they have for compressed liquid is 5 megapascal, and here we have only 1 megapascal. So our way to get around it is we always go ahead to approximate. So approx. How do we approx? We are trying to find the entropy. So we're going to use saturated liquid at this particular temperature, 50 degrees Celsius, to approximate, right? Because it's a compressed liquid. We don't have the tabulated data, so we want to get a value. We approximate using saturated liquid. However, we have to use temperature table because liquid is not compressible, unlike the air, right? It's not compressible. So it does not change too much with pressure, right? However, it changes more with temperature. That's a reason behind why using the temperature table. So temperature table, that would be table A4. So from table A4, we're going to write down at 50 degrees Celsius, and we're using SF, so which is that value. So S is going to be equal to 0.7038 and kilojoule per kilogram per Kelvin. So that's our second solution, a second condition for this one. So we're done with that. Again, move on to look at the third one. We given pressure and temperature again. All right, let's move on. So table A5, we want to find out what's going to be the saturated temperature at 1.8, right? Tsat at 1.8 megapascal. And we come to table A5 and realize there's no 1.8. The closest we have is 1.5 and 1.2, but you know, theoretically you want to do linear interpolation, but this one, so far you don't need to, because look at it. Even if it's 2 kilopascal, the saturated temperature, I'm looking at 2. I'm going to look at 1.8 mega, so that's 1800, right? Okay, because I'll go down to 1800. Sorry for the mistake there. So if it's 1800, it's around here between those two values. Look at it. Both of those temperature is around 210. And this temperature is 400. So I don't need to do the linear interpolation to find exact value because that's not relevant. So I will say it's around 210. However, our temperature here is 400 degrees. Way greater than this Tsat. Then we know this is going to be superheated vapor. Because at superheated vapor region, the temperature is greater than the saturated temperature. So knowing that, we want to go to find our S. Then we need to go to table A6, superheated vapor. And knowing the condition is 1.8 megapascal. Okay, we do have a 1.8 megapascal table and 400 degrees Celsius. So look around, look down, look across, we find our S. S here is going to be equal to 7.1814. Okay. And that's going to be in kilojoule per kilogram per Kelvin. Okay. All right, now let's look at our problem 4. They give us a pressure, they give us quality. Whenever quality is given between 0 and 1, we know it's a saturated liquid and vapor mixture. So given pressure, we go to table A5, the pressure table. At 40 kilopascal, we can find the saturated temperature right away. So we can see this is going to be 75.86 degrees Celsius. Then how do we find our S based on the quality? We're going to write down our formula. It's the same thing we used to find other intensive property before, like internal energy, enthalpy, etc. So S will be the same logic. So it's SF plus X SFG. Okay, so at 40 kilopascal, our SF is this value, 1.0261. And the quality we'll be using is 0.9. That means 90% of them are saturated vapor, with only 10% being liquid. And times SFG, which is this value, 6.6430. And when we calculate it, it's about to be 7.0056. Okay, the unit is kilojoule per kilogram per Kelvin. All right. So the next thing I want to look at is this condition. They give us S and they give us a pressure. Well, we are still at 40, okay? And look at the 40. Since they give us S, we're going to compare this S with this SF and SG. and that's what we're going to do. We realize this S given, it's 7.1794, and our SF is 1.0261, and our SG is what? 7.6691. So that means our S is in between SF and SG. When would that happen? It happens with some saturated liquid vapor mix. So in that situation, we need to find our quality. And the quality equation will be like what we had before, S minus SF over SFG. And this given S is 7.1794, and SF is 1.0261, and SFG is 6.6430. And that will help us to calculate the quality. And I have the answer here. It's about that value. Okay. And the last thing they want you to find out in the table is what's going to be the temperature, right? So you know it's a saturated liquid vapor mix. Then during that horizontal line, the temperature stays constant at the saturated temperature at 40 kilopascal. Then you will have 75.86 degrees Celsius right here, right? Okay, so now we have using steam table to look for, to solve the problems, to evaluate S. And so in the next video, we will looking at some other concepts, and such as entropy change. So bye now.